Hi, so what are vectors and why are they important? That's kind of what we'll get into today. And it turns out that almost every lesson in this class, multivariate calculus, is really going to depend on vectors. So what we're talking about today is really going to build the foundation for pretty much every lesson in the rest of the class. So I'd encourage you, it may seem kind of basic, I definitely encourage you to keep your focus, because if you get this down, you get the notation down, and these concepts, it's gonna help you out through the rest of the class for sure. But what is a vector? Well, if you want to think about it, say in terms of a satellite orbiting, you could use a vector to describe the position of the satellite. You could also use a vector to describe the velocity of that satellite as it orbits the Earth, or you could use a vector to represent the force acting on that satellite or its acceleration. So perhaps of these three examples, the idea of the velocity might be the most intuitive use of a vector, because if you think of velocity, you think of, okay, I've got a certain speed and I got a certain direction. I'm going 60 miles per hour and I'm going north on I-25. And those are really the two key components of a vector. You've got the magnitude, or in the case of velocity, the speed, but more generally the magnitude, and then you have the direction. And it turns out a vector is actually a type of tensor, sort of a broader category, and another type of tensor is a scalar, which you may be more familiar with, and that's just like a number, the number 5, it's a scalar. And scalar, of course, have less information than a vector. They just contain that sort of that magnitude piece of information. They don't have that direction associated with them. And that direction that vectors have, it can be in 2 or 3 dimensions, and just for this video we'll focus on the 2D part. So some things we're going to hopefully introduce here. We're going to describe what a vector is and why we use it, and then classify some geometric relationships of vectors. So those are the objectives for this video. So let's start off by imagining a vector given in component form. We'll call it A, and it's going to have the dimensions 1 and 2. And just a word on notation here. You'll typically want to express a vector with this sort of accent over it. You'll see in the book sometimes the notation is bold. If you see that in textbooks sometimes, but if you're writing it out, you can't really make something in bold. So you may see it both ways, but definitely with your communication, I would advise you to just put that accent over to denote that it's a vector. And it would look like this in our typical XY plane. So we start at the tail, or the initial point, which we'll just assume is at 0, 0 for now, and we move over 1 in the positive X direction, and we move up 2 in the positive Y direction. And doing that, we arrive at the vector's tip, or terminal point. So what is the difference between this vector and, say, the point B, which is at 1, 2? Well, they're related because we could think of the vector as connecting our points. It's called the origin A, the tail, with the point B, 1, 2, its tip. So in a sense, the point 1, 2 represents the tip of our vector A, which we could describe also as the vector connecting A and B, or generally we could call it A sub 1, A sub 2, where A sub 1 is equal to 1 and A sub 2 equals to 2. But let me put another vector up here, and we'll start at this point 1, 0 instead of the origin. Now tell me, how are these two vectors different? Well, we said that a vector had two quantities, right? It's got magnitude and it's got direction. So let's take a look at the magnitude of these vectors. You may kind of know the answer of whether they're different or not, but since we're talking about magnitude, let's just go into how we'd find this. And it's pretty simple, as you might imagine. It's basically just forms a triangle, and we can use the Pythagorean theorem, and we'll denote our magnitude as A with these brackets around it. And since our x and our y coordinates are orthogonal, we know it's a right triangle, where this hypotenuse can be found as the square root of the addition of these lengths squared. So our magnitude of A is going to equal the square root of A1 squared plus B1 squared quantity, which is equal to the square root of 1 squared plus 2 squared, which is equal to the square root of 5. So You can tell both of these vectors are going to have the same side length, so both of their magnitudes obviously are going to be equal. We kind of tell it by looking at it. And how about their directions? Are their directions the same? Well, yeah, they're both pointed in the same direction. They both go over 1 and up 2. So they have the same magnitude and the same direction. So it turns out they are actually the same vector. They're equal. We call them equal or equivalent. But they're obviously different though, right? So the difference obviously is that initial point. But since they have an initial point, we can actually still distinguish them by calling this the position vector, the one that starts at the origin. So we can add a descriptor to it. Or we could specifically identify this other one as having an initial point of 1, 0. And either way, you've got to sort of add another descriptor if you want to identify that initial point. So that's the basic intro to what vectors are and when they're equal. And next we'll talk about some basic operations that we can do with vectors.